Hello everybody, I have a problem for you. It's a problem about conservation of energy. So let's consider Bob, whose mass is 70 kilograms, and Bob is going to ski down a 25-degree slope. He's going to start from rest at a height of 40 meters above the bottom, and we also have a strong wind that is blowing horizontally with a force of 150 newtons. So the idea is to use energy work to find Bob's speed at the bottom of the hill. In this problem, just to make things a little easier, we're going to assume that there is no friction. So the coefficient mu sub k is going to be equal to 0. So let's start by drawing a picture of the situation. I also copied the statement of the problem on the right if you need to refer to it again. So we have the slope there, we have a little figure there that represents Bob at the top of the hill, and I'm putting in the picture some information. I have the 40 meters height of the slope of the hill from which Bob is starting. The angle of the slope is 25 degrees, mass is 70 kilograms, and we have a wind, horizontal wind, of 150 newtons. So that's our picture. What are we looking for in this problem? They're asking us to find Bob's speed at the bottom of the hill. Alright, so we're going to use conservation of energy for this problem. So the basic equation for conservation of energy tells us that if there are external forces acting on a system and those forces do work, then the amount of work done by the external forces should be equal to the change in the energy of the system. The energy of the system must be computed by adding all the different forms of energy. So we have kinetic energy, potential energy, thermal energy, chemical energy, and several other different kinds of energy. And the change in energy, therefore, is the sum of the change in the potential in the kinetic energy, plus the change in the potential energy, plus the change in the thermal energy, etc. We add all of the possible changes that occur in the system between the initial situation and the final situation. For this particular problem, we have no changes in thermal energy, and that's because we don't have any friction, and we're going to assume that there is no air drag. There's no changes in chemical energy. We don't have any kind of fuel that we're burning. There's no machine here. So all of the other forms of energy are not really relevant for this problem. They are not changing. So the change in energy is going to be given by the change in the kinetic energy and the change in the gravitational potential energy. The system that we're going to assume here is Bob. So if Bob is the system, the external force acting on Bob, the only external force that can do work on Bob is going to be the wind. The force of the wind is the external force acting on the system. You might think of the normal as being an external force, and that is correct, but the normal force is not going to do any work because the normal is perpendicular to the displacement. So the only external force here that we have doing work is the force of the wind. So our equation says that the work done by the wind on Bob is going to be equal to the change in the kinetic energy of Bob plus the change in the potential energy of Bob. The change in the kinetic energy is defined as final kinetic energy minus initial kinetic energy. The initial kinetic energy is 0 because the statement says that Bob starts from rest. The change in potential energy is the final potential energy minus the initial potential energy. Since we are calculating the velocity of Bob at the bottom of the hill, we can assume that the bottom of the hill has a height equal to 0. So the final potential energy is going to be equal to 0. So the change in energy is going to be 1/2 of the mass times the velocity at the end square minus mgh. That came from the change in potential energy being u final minus u initial. The minus is because we do final minus initial, and the final potential energy was 0. If there had been no wind, then the equation would say that the work done by the wind is 0, and therefore the 1/2 of mv squared will be equal to mgh, which is the usual conservation of energy equation that we would have written in the case when there is no friction and no external forces. So we say the potential energy at the top equals the kinetic energy at the bottom. That's what we would have had in that situation. So here we don't have that. The difference between the kinetic energy 1/2 mv squared and mgh is going to be the work done by the force of the wind. The height of the hill is 40 meters. So if you think about the equation that we have there, we have a lot of information in this equation. We're moving in the next step. We're moving the mgh, which has a minus on the right hand side of the equal sign. We're going to move it to the other side. So the 1/2 mv final square is going to be equal to mgh plus the work done by the wind. In this equation we have the Bob's mass that's given, it's 70 kilograms. Putting a check mark next to the variables that I know its value. The final velocity is what we're looking for. That's the question in the problem. Mass, as we said, we know it. G is 9.8. The height is 40 meters. And what we need to calculate now to do our calculation for the final velocity, for Bob's final velocity at the bottom of the hill, would be we need to calculate the work done by the wind. So that's going to be our next step. So by definition, the work done by force is the dot product between the force vector and the displacement vector. So that's the force of the wind, which is a vector, points in a specific direction, in this case to the left, and the displacement vector, which is the vector that points from the initial location to the final location. It's a dot product between those two vectors. That's how the work is defined. The dot product between two vectors can be expressed as the magnitude of one vector, that would be the magnitude of the force of the wind, times the magnitude of the other vector, in this case the displacement vector, so what distance was covered between the initial and the final, and we need the cosine of the angle between those two vectors. So the distance, let's think about the distance. So how do we calculate the distance traveled by Bob from the top to the bottom? So if the height of the hill is 40 meters and the angle is 25 degrees, then delta S is the hypotenuse of that right angle triangle. So the hypotenuse multiplied by the sine of 25 degrees should be equal to the opposite side, which is 40 in this case. So delta S times sine of 25 is 40 meters. Therefore delta S is 40 divided by sine of 25. And if you plug in the numbers, you get delta S is 94.6 meters. So that, now we know the distance that Bob travels. So that gives us, for the work, we can use the force of the wind is 150. We have delta S now, 94.6. The only thing missing to be able to calculate the work done by the wind is the angle between the force, the wind force, and delta S. So I'm drawing the force vector at the bottom, so it points to the left. The displacement vector delta S points down and to the right, and we need the angle between those two vectors. Okay, so to find that angle, just consider that delta S makes 25 degrees with the horizontal. So the angle between those two between the top dash line and delta S vector is 25. Also, the angle between delta S and the bottom horizontal line, that's 25 degrees. So theta is clearly 180 minus 25. 180 minus 25. So 180 minus 25 is 155. So the angle between the force of the wind vector and the displacement vector is 155 degrees. So now we're ready to plug in that in our equation. So the work done by the wind is going to be 150 newtons multiplied by 94.6 meters multiplied by the cosine of 155 degrees. Plug in the numbers in your calculator, you get the work done by the wind is minus 12,860 joules. So we basically have everything that we need to find the velocity, the final velocity. So if we rewrite this equation, plugging in all the things that we already know. So the mass is 70 kilograms, so 1/2 of 70 times the final velocity square is going to be equal to mgh. So m is 70, g 9.8, the height was, we said, was 40, and the work done by the wind is a negative work of 12,860 joules. So we put that in our equation. The right hand side has a numerical value of 27,440 minus 12,860, which gives 14,580 joules. We divide that by 35, which gives us 416.6, and we take the square root of that to solve for the final velocity. So square root of that number gives us our final answer of 20.4 meters per second, which is about 45 miles per hour. So Bob reaches the bottom of the incline with a speed of about 45 miles per hour. Alright, so I hope that is helpful, and I'll see you in the next video.